Hi everyone, this is Kalyan Kumar with another video on name reactions, and today is the turn of the alphabet B and we start with Baeyer-Villiger oxidation. So let's understand what is Baeyer-Villiger oxidation, and then we'll try to figure out the mechanism and when all is this going to happen. Well, Baeyer-Villiger oxidation is basically an oxidation reaction in which ketones are converted into esters. Very important reaction for ketones. This is the only reaction for ketones which can convert them directly into ester by a single reaction sequence. And if you use an aldehyde, now the reason I'm specifying ketones is because if you use aldehydes, well, aldehydes will become carboxylic acid. Now, as you can notice, what is basically happening is that oxygen is getting in between the carbonyl carbon and one of the groups attached to the carbonyl carbon in the ketone. In the case of an aldehyde, it is attaching with, it is going in between the carbon and the H, giving you a carboxylic acid. Generally, we do not talk about the Baeyer-Villiger oxidation of aldehydes for the simple reason that aldehydes can be converted into carboxylic acid by a variety of other reactions also. Reaction with alkaline, hot alkaline KMnO4, even that gives you carboxylic acid. So this reaction is very important as far as ketones are concerned, because this is the only reaction that will convert a ketone into an ester. So let's look into the definition of Baeyer-Villiger oxidation. Baeyer-Villiger oxidation is the oxidative cleavage of a carbon-carbon bond adjacent to a carbonyl, which converts the ketones to esters and cyclic ketones to lactones. And Baeyer-Villiger oxidation is generally carried out by peroxy acids. It can be carried out with peroxy acids such as MCBPA and trifluoroacetic acid, BF3 with H2O2 or H2O2 with a base. So let's understand what is a peroxy acid. A peroxy acid in general is something which has a peroxide linkage. A normal carboxylic acid looks like this. A peroxy acid looks like this. There is another O here. So this is the peroxide linkage of peroxy acids. MCBPA is metachlorobenzoic peracid. So this is metachloro and this is a peroxy acid similar to this part. So it's metachlorobenzoic peracid, and this is trifluoroacetic acid, BF3 with H2O2, H2O2 in the presence of base. So let's look at the reaction now. This is the ketone you have. I'm reacting this with a peroxy acid, and look at the product formed, an ester. Of course, it remains to be seen which R will the O get inserted in between. Will it be R prime or the R? Of course, that depends upon the nature of these two, and that we will discuss soon. The group that migrates on to this carbon, the group which migrates to oxygen rather, or the group that gets attached to oxygen, is the one which has higher migrating aptitude. And higher migrating aptitude is generally decided by stereoelectronic effects. And at the end of this reaction mechanism, I'm going to discuss what is stereoelectronic effect. So just wait for a while and I'll explain to you what that basically means. Now, if you take acetophenone, now acetophenone is basically this one. Now, if you remember the migrating aptitude of various groups, you will realize that a phenyl group migrates better than a methyl group. Now, why it does so, that we will understand very soon, but phenyl group does migrate better than methyl group. So the O gets inserted here. The O gets inserted between carbonyl carbon and that R group whose migrating aptitude is higher. So, for example, acetophenone on treatment with peroxy trifluoroacetic acid gives phenyl acetate and not methyl benzoate. this reflects on the phenyl group having a greater migrating tendency than a methyl group, as we just discussed. So here we have acetophenone and reacting with trifluoroacetic acid, and as you can see, it gives you phenyl acetate. Now it is basically, one can say, it's the insertion of oxygen. Oxygen is getting inserted in between the carbonyl carbon and one of the R groups. So the overall reaction is an insertion of oxygen atom between the carbonyl group and the group that has a greater migrating tendency. So first of all, we're going to look at the mechanism. Step 1 involves the transfer of proton from the peroxy acid to the oxygen of the ketone. The first step involves transfer of acidic hydrogen from peroxy acid to carbonyl oxygen. It goes like this. You have the ketone here. So you can see the lone pair on oxygen. And this is the peroxy acid. The lone pair of oxygen picks up the H. And the OH bond goes to O. And you find that the ketone has taken in the H and the anion leaves. Trifluoroperoacetate ion. So that is how it leaves. In the second step, this O minus is going to attack this carbon. Step 2, the second step involves attack of peroxy anion on the carbonyl carbon. So as you can see, this has a resonating structure like this, and the positive charge is on carbon. This anion attacks this electron deficient oxygen. Now one might ask, why does this O minus attack the carbon and not the oxygen, since both of them contain a positive charge? That's because this oxygen is not electron deficient. The positive charge is only because of the coordinate bond that it forms. Its octet is complete. It doesn't need any electron. Whereas this carbon is electron deficient. It's got only 6 electrons. One orbital is empty. That is why it attacks the carbon and not the oxygen. So now what are we going to have? We're going to have the O attached to the carbon. In the third step, what happens is, and this is the rate determining step and the very important step, the OO bond breaks, because remember, it has got lone pairs. The OO single bond is a very weak bond because the repulsion between the two lone pairs on oxygen, and that would make this bond very weak and it breaks in favor of the O on the right side. So that is step 3. So step 3, in the third step, the oxygen-oxygen linkage cleaves as it is weak due to lone pair repulsion to relate the trifluoroacetate anion, which is in fact a good leaving group because the minus charge gets attached to 2 oxygens now because of resonance. It goes on to 2 oxygens, and moreover the 3 fluoro will pull the electron toward themselves by minus I effect that will make the anion even more stable. So it's a very good leaving group, and the oxygen in fact becomes electron deficient. And that is why it's a rate determining step, because oxygen, being highly electronegative, does not want to become electron deficient. So it's difficult for this reaction to happen, this particular step to happen. So here the O becomes plus. Now in the next step, another important thing happens, migration. And this is where the migratory aptitude comes, because one of the groups from the carbon will migrate to oxygen so that the plus comes down to the carbon, because carbon can accommodate a positive charge much better than oxygen, because carbon is less electronegative. So one of the alkyl or aryl groups will go to O. So step 4, in the fourth step, the phenyl group migrates on the electron deficient oxygen from the adjacent carbon to give a carbocation. So this migrates to O and the C becomes positive. But as you can see in step 5, and of course this has a resonating structure, the lone pair on oxygen will try to make the octet complete by resonating with oxygen, and in the last step this particular proton is released. Step 5, in the fifth step, the positively charged oxygen atom loses a proton to give phenyl acetate. So as you can see, the proton leaves and you get phenyl acetate. Now comes the very important part, something that we were intending to discuss later on. And this is where we're going to talk about the stereoelectronic effects. Migrating aptitude, hyperconjugation, all these things are explained based on stereoelectronic effect. And the migrating group especially is decided both by steric as well as stereoelectronic effects. So let us understand what is a stereoelectronic effect. Stereoelectronic effect is an effect which determines the physical and chemical nature and behavior and preferences of molecules, and this is because of the overlap of atomic or molecular orbitals. So stereoelectronic effect is the effect on molecular structures, physical properties and reactivities due to a molecule's electronic structure, in particular the interaction between atomic or molecular orbitals. Let me clarify this a little bit now. What we are basically saying is that electrons from a lone pair or bond pair tend to overlap with empty orbitals. And I'm talking about generally molecular orbitals because we are talking about molecules now. So this molecular orbital theory is not as easy as the valence bond theory to understand. But basically what we are trying to say is the stereoelectronic effect is an effect in which you tend to find overlap between the lone pair or bond pair of molecular orbitals to empty molecular orbitals. Typical stereoelectronic effects involve specific orbital overlaps which generally lead to a specific molecular conformation or creates energy differentiation among various transition states that lead to a particular reaction selectivity. Now what we are basically trying to say from this particular point is that if you are aware of what is known as the Gauss effect, the Gauss effect is basically an effect in which if you have highly electronegative, let's say you have 1,2-difluoroethane, then 1,2-difluoroethane has the more stable Gauss form than the anti-form. This is the anti-form. The Gauss form is more stable than the anti-form, even though generally anti-forms are more stable. So from the steric point of view, this has to be more stable, but it is this which is more stable. That is because the molecular orbital of this CH overlaps with the anti-bonding orbital of the CF because they are anti. So it's like something like this. Carbon-carbon connection, an empty orbital here. Sorry, I think I need to erase this because the orbital has to be down. The anti-bonding orbital is down and there is an overlap. So the CF bond is here, its anti-bonding orbital is down. The CH is here, its bonding orbital is down and the anti-bonding orbital is here. And there is an electron transfer from here to here. Looks a little bit difficult to understand why they do that. But remember, electron is a wave, it's not a particle. That is the very basis of molecular orbital theory. So electrons tend to go, it's just like resonance, because this is filled and this is empty and there are alternate positions in between a single bond. So there is an overlap here, kind of a resonance. And that resonance helps stabilize the Gauss effect. This is basically stereoelectronic effect. So I'm going to explain this a little bit more so that you'll be able to really understand what I'm talking about. The behavior of a molecule is not only established by steric, inductive and mesomeric, it is also induced by these stereoelectronic effects. So the stereoelectronic effect, along with the steric, inductive and mesomeric effect, is one of the key theories in illustrating unusual selectivity, reactivity and stability cases in the course of organic chemistry. The very fact that the gauche form was more stable than the anti-form said that the steric effect was not that important as the stereoelectronic effect. Now let us understand stereoelectronic effect a little bit in detail. Let's get it in a way so that we are able to relate to it. Now, when a molecule is formed, molecular orbitals are created from atomic orbitals. I think we know that, so we don't have an issue with that part. But there's a misconception. The misconception is everybody believes that all molecular orbitals bonding have to be lower in energy than all the anti-bonding molecular orbitals. That's a misconception. It is a misconception that bonding molecular orbitals are always lower in energy than antibonding molecular orbitals. Now this is true only if both are formed from the same set of atomic orbitals. So if there are two atomic orbitals here and here, they give rise to antibonding, they give rise to bonding. So bonding is always lower than antibonding. But remember, that is only because these two are created from the same set of atomic orbitals. But suppose I have higher atomic orbitals. Now they will also have bonding, they will also have antibonding, but can you notice that this bonding is higher in energy than this antibonding? So it is not necessary to believe that all antibonding will be higher in energy than all bonding. It is only that antibonding and bonding which will be bonding is lower and antibonding is higher when they are formed from the same set of atomic orbitals. And what would happen if the energy of the atomic orbitals is also not same? If they are different atoms, then you're going to have high level of complication. So anything is possible in this case. This is true only for those bonding and anti-bonding molecular orbitals that form from the same set of atomic orbitals. So from the same set of atomic orbitals, if a molecular orbital is formed and an anti-bonding, a bonding molecular orbital is formed and an anti-bonding molecular orbital formed, only then we can say anti-bonding has to be higher in energy. Not if they are formed from different sets of atomic orbitals, and that too with various atoms, different atoms. So the next point is that generally atomic orbitals of higher energy lead to bonding orbitals that have higher energy than the anti-bonding molecular orbitals from the orbitals of lower energy. That means if I have a 1s, it will have bonding, anti-bonding. If I have 2s, the bonding of 2s is higher energy than the antibonding of 1s. So atomic orbitals of higher energy lead to bonding orbitals that have higher energy than antibonding molecular orbitals formed from atomic orbitals of lower energy. Okay. Therefore, it is possible that the bonding orbital of one bond, CH bond, bonding, is higher in energy. This is energy. It's higher in energy, whereas the anti-bonding of CS may be lower energy. Now, of course, one will not be able to explain why this is so. This is based on pure calculation, because molecular orbital theory is not a qualitative theory. It's a quantitative theory. It is based on measurements that we write the orbitals, the molecular orbitals in a particular order of energy. And if you remember, the order of energy does not remain the same in every case. It keeps changing. That is because it's a quantitative thing. You cannot predict it qualitatively. So if the bonding orbitals has 2 electrons and the anti-bonding of CF is empty, then it is going to stabilize the molecule if the electron gets poured from higher energy to the lower energy. This is anti-bonding and this is bonding. So the bonding electrons of CH, the bonding molecular orbital, overlap with the anti-bonding orbital of CF, and thereby you find there is a resonance, an overlap, and this tends to make this molecule more stable. So more of the H would tend to remain anti to F rather than F remaining anti to F. Moreover, if the atomic orbitals belong to different atoms, then the situation becomes more complex. It would suffice to understand that some bonding or non-bonding molecular orbitals have energies higher than some anti-bonding molecular orbitals. Stereoelectronic effect generally involves a donor-acceptor interaction. The donor is usually a higher bonding or non-bonding orbital, and the acceptor is often a low-lying anti-bonding orbital as shown in the following diagram. So this is the energy axis. This is the bonding molecular orbital between two atoms A and B. This is the anti-bonding molecular orbital formed between two different atoms C and D. So if A and B and C and D are different, then definitely it's possible that the anti-bonding of the C and D could be lower energy than the bonding. And if the anti-bonding is empty and the bonding is filled with electrons, then it makes sense. And if they are alternate, conjugated, then resonance will happen and the electrons will flow from the higher energy to the lower energy. And that would make the molecule more stable. This is stereoelectronic effect. Now let's understand how does this stereoelectronic effect work in Baeyer-Villiger oxidation. The stereoelectronic effect in the Baeyer-Villiger oxidation refers to the necessity of the oxygen-oxygen bond in the peroxide group to be anti-periplanar to the group that migrates. We'll understand this. This orientation facilitates optimum overlap of the sigma orbital of the migrating group to the sigma star anti-bonding orbital of the peroxide group. Let's understand this. What I'm saying is, remember, the migration happens when the OO bond cleaves. Okay, we have a situation like this. We have something like this, and there is a single bond OH here. There is R prime here, and this was the peroxide that was linked. And remember, this bond was getting broken. Now, the conformation in which this breaks, remember, this breaking and migration occur simultaneously. And what happens is, if I draw the conformation between this oxygen and this carbon, if I draw the conformation here, then it is seen that that group migrates on this O, which is anti to this bond. The O bond, the group R prime or R, will migrate to this O if it is anti to this bond. Rather, since the rotation is free here, even R prime can come to the anti part and even the R can come. What I'm basically trying to suggest here is, the stereoelectronic effect dictates that the conformation on which the migration happens when the migrating group happens to be anti to this OO bond. For example, look at this. I'm drawing the conformation between O and C, and this O is the front O. And as you notice, there is a single bond O, and this O is attached to COR, and there is a group R1 on this carbon. The carbon is the one with the circle. So on this carbon you have a R1, you have a RM, which is the migrating group, and you have a OH. And the migration happens when the migrating group becomes anti to this. Why? Why does it happen only in this particular step when the group that migrates has to be anti to this? That is because in this orientation, this conformation is one of the most stable conformations. Why is it more stable? Because in this conformation, there's an optimum overlap of the bonding molecular orbital of the migrating group. That means this RM, remember, it's attached to this carbon. This RM is attached to carbon. So carbon, RM, oxygen, peroxide linkage. the bonding orbital and the antibonding empty of oxygen overlap. Remember, the general stereoelectronic effect occurs between the antibonding of a highly electronegative element and between a carbon H bond or a carbon-carbon bond. The bonding orbitals of these are filled, the antibondings of these fellows are empty, and they happen to be lower in energy than these, and therefore the electron gets poured here. So Rm tends to be anti to the peroxide bond. And it is that time when the Rm moves to O and this bond breaks, and this Rm tends to go and attach to O. And another reason is steric effect. And this implies that Rm should have electron releasing tendencies, because only if it is going to have electron releasing tendencies will it be able to pour the electron into the empty antibonding orbital of this particular bond. It is indeed found that releasing groups on Rm tend to make it migrate better than withdrawing groups on it. And moreover, if Rm is bulky, makes more sense for it to remain anti to O. So bulkier groups tend to migrate better than non-bulkier groups, because this particular conformation becomes more stable if the bulkier group is anti to OO bond. So moreover, the bulkier Rm is, more stable the conformation shown would be, as it is far away from the bond pairs and lone pairs of O. Thus, the reaction establishes the migratory aptitude of various alkyl groups and H as H tertiary, secondary, primary methyl, and that of aryl groups as anisole, the tolulyl group. These are releasing groups. Anisole is basically a group in which O gives the lone pair to the benzene ring. P-tolulyl is the one in which methyl group gives through hyperconjugation. Then you got phenyl. Now you got the withdrawing p-chloro, para-nitrophenyl. So these are withdrawing, and that's why their migrating tendencies are much lower. And in the case of both ketones, generally it is the aryl group which migrates, except when the carbon is tertiary. In the case of tertiary carbon, it is the tertiary carbon which migrates compared to the aryl group. That's because this is bulkier. So here the steric effect becomes more prominent. So if you look at a reaction between a tertiary carbon and a phenyl group attached to the carbonyl carbon of a ketone, you know the O will get inserted between the tertiary carbon and carbonyl carbon. So this is the product formed. And if you take cyclic ketones, for example, cyclic ketones will become lactones because O will get inserted. So cyclic ketones get converted to lactones with ring expansion on treatment with peroxy acids. So if I have cyclopentanone, it forms a lactone. And that becomes 6-membered because O gets inserted. So this is Baeyer-Villiger oxidation. And if you haven't got it properly, go through the video as many times as you want. You'll be able to get it. If you have any questions, any queries, any doubts, anything that is not clear, please drop them in the comment section below. And subscribe to my channel to get more videos of this kind. Thanks for watching.